Everyone, today we are going to analyze this beam using stiffness matrix method. Before analyzing, let's see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 45 kN acting at 2 meter from the point A. In the span BC, we are having UDL 15 kN per meter acting for the full span. In the point A, we are having a fixed support. In the point B and in the point C, we are having hinged supports. Span AB is 6 meter long and span BC is 4 meter long. The moment of inertia for the span AB is 1.5 I. For the span BC, the moment of inertia is 2I. In this beam, we have to find three moments. In the point A, we are having a fixed support. In the fixed support, there will be a moment, that is MAB. In the joints, there will be two moments. In this beam, we are having a joint, that is joint B. In the joint B, we are having two moments, MBA and MBC. In the point C, there will be no movement because it is a simply supported end. So MCB is equal to 0. So totally we have to find three moments, MAB, MBA and MBC. Also we have to find three reactions, RA, RB and RC. Now let's make the fixed end moments. First, let us make the fixed end moments in the span AB. For making the fixed end moments, we have to assume every span as a separate fixed beam. You can see that I have made the span AB as a separate fixed beam. Now let's see the formulas to find out the fixed end moments. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, there is a point load. That point load is not acting on the center, so we have to select this condition. The formulas for the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. In the span BC, there is UDL acting for the full span, so we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. Now let's apply the formula and find out the fixed end moments. In the span AB, the point load is not acting on the center. We already saw the formulas. Let's apply the values inside the formulas. W is 45, A is 2, B is 4 and L is 6. After calculation, we are getting M of AB is equal to minus 40 kN meter and M of BA is equal to 20 kN meter. Now let us make the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We already saw the formulas for the fixed end moments. Let us apply the values inside the formula. W is 15 and L is 4. After calculations, we are getting M of BC is equal to minus 20 kN meter and M of CB is equal to 20 kN meter. In the stiffness matrix method, we have to find the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. And in the roller support also, there will be slope. In this beam, there are two hinged supports. In the point B and in the point C, we are having hinged supports. So, the number of supports where slope occurs is 2. In the point B, we are having theta B and in the point C, we are having theta C. So, in this problem, we are having two unknowns. If we calculate these two unknowns, we can find the final moments very easily. Now let us make the fully restrained structure. In the fully restrained structure, there will be no slope. We know that only in the fixed support there will be no slope. So let us remove the hinged supports from the point B and from the point C and replace them with the fixed supports. In this structure, there will be no slope because all of the supports are fixed. That is why it is called the fully restrained structure. We have made the fully restrained structure. Now let us make the coordinate diagram. In this problem, we are having two coordinates. In the point B and in the point C, we are having coordinates. Because in these points only we had slope and we replaced the supports in these points by fixed supports. Now let us see the formula to calculate the slope values. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix. In this formula, PL matrix is the moments developed in the coordinates due to the given load. P matrix is the final forces acting in the coordinate direction. K matrix is the stiffness matrix. In this formula, now let us calculate the PL matrix. We know that the PL matrix is the moments developed in the coordinates due to the given load. In this analysis, we are having two coordinates. In the point B and in the point C, we are having the coordinates. In the first coordinate B, we have calculated two fixed end moments m of BA and m of BC. We have to add them. After adding, we are getting 0. In the second coordinate C, we have calculated a fixed end moment, that is m of CB, which is equal to 20. Finally, we have made the PL matrix. The size of the PL matrix will be according to the coordinates. In this problem, we are having two coordinates, so there will be two values inside the matrix. In this formula, now let us find the P matrix. If in the beam there is overhanging, we have to calculate the P matrix. If in the beam there is overhanging, we have to calculate the P matrix. Otherwise, we can simply enter 0. In the given beam also, there is no overhanging. So, we can simply enter 0, 0. The size of the P matrix will be according to the coordinates. In this problem, we are having two coordinates. So, inside the matrix, we will have two values. Both of the values are 0 because there is no overhanging in the given beam. In this formula, we have calculated the PL matrix and the P matrix. Only one is remaining to be calculated, that is the stiffness matrix. Now let's see how to calculate the stiffness values. To calculate the stiffness values, we have to apply unit displacement, that is theta is equal to 1 radian in every coordinate. In this analysis, we are having two coordinates. In the point B and in the point C, we are having coordinates. So, we have to apply the unit displacement in these coordinates. Then, we have to use the formulas. If the Farad is fixed, the formula is 4EI upon L. If the Farad is hinged, the formula is 2EI upon L. We have to apply the unit displacement in the restrained beam, not in the given beam. Now let's see the size of the stiffness matrix. For 3 coordinates, the size will be 3 by 3. For 2 coordinates, the size will be 2 by 2. For 1 coordinate, the size will be 1 by 1. In this problem, we are having 2 coordinates. So the size will be 2 by 2. Inside the matrix, we will have 2 rows and 2 columns. To calculate the first row, we have to apply the unit displacement in the first coordinate, and to calculate the second row, we have to apply the unit displacement in the second coordinate. Now let us apply unit displacement in the first coordinate, that is the point B. In the point B, we are having a fixed support, but when we apply unit displacement, it is no longer a fixed support, it becomes a hinged support. Because in the fixed support there will be no displacement, but we are applying unit displacement, that is why the fixed support becomes a hinged support. Both of the coordinates should be in the clockwise direction. You can see that both of the coordinates are made in the clockwise direction. Now let's see how to make this slope curve. We are applying unit displacement in the point B. The point B is a joint. It is connecting two spans. So from the joint B, we have to make two clockwise curves. One curve towards the point A and one curve towards the point C. Both of the curves should be in the clockwise direction. Now we have to see the direction of the arrows. This arrow is indicating upwards. That means the slope curve will come above the span. This arrow is indicating downwards. That means the slope curve will come below the span. In the fixed support, there will be no slope. In the point A and in the point C, we are having fixed supports. So we must give some gap between the slope curve and the fixed supports. You can see that I have given some gap between the slope curve and the fixed supports. Now let us calculate the stiffness values. The stiffness values should be calculated in the order, first from the first coordinate, then from the second coordinate. For that, from the point B, we have to look on both the sides. On the left side, we are having a fixed support. If the Farad is fixed, the formula is 4EI upon L. For the span AB, the moment of inertia is 1.5I. So instead of I, we have to apply 1.5I. The length is 6 meter. Let's apply that. Now let us look on the right of B. On the right of B also, we are having a fixed support. So we have to apply the same formula 4EI upon L. The moment of inertia for BC is 2I. So instead of I, we have to apply 2I. The length is 4 meter. After adding these two values, we are getting 3EI. Now let us calculate K12. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, we are having a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. For CB, the moment of inertia is 2I. Length is 4 meter. Let us apply both of them. Finally, for K12, we are getting EI. In the stiffness matrix, we have made the first row. Now let us make the second row. For that, we have to apply the unit displacement in the second coordinate, that is the point C. In the point C, we are having a fixed support, but when we apply the unit displacement, it is no longer a fixed support, it becomes a hinged support. Now let's see how to make this slope curve. We are applying unit displacement in the point C. So from the point C, we have to make a clockwise curve towards the point B. Then we have to look the direction of the arrow. This arrow is indicating upwards. That means the slope curve will come above the span. In the fixed support, there will be no slope. So we have to give some gap between the fixed support and the slope curve. That is why the slope curve ends before the point B and can't continue after the point B. Now let us calculate the stiffness values. The stiffness values should be calculated in the order, first from the first coordinate, then from the second coordinate. Now let us calculate K21. For that, from the point B, we have to look on both the sides. On the left side, there is no slope curve. If there is no slope curve, there will be no stiffness. On the right side, we are having a hinged support. If the far end is hinged, the formula for the stiffness is 2EI upon L. Here, the moment of inertia is 2I and L is 4 meter. Finally, we are getting EI. Now, let us calculate K22. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, we are having a fixed support. If the far end is fixed, the formula is 4EI upon L. Here, the moment of inertia is 2I and length is 4 meter. After the calculation, we are getting 2EI. In the stiffness matrix, we have calculated both of the rows. We can apply the values. EI is common for all of the values, so let us take it outside. In the system displacement formula, we have calculated all of the values. We have calculated the stiffness matrix, P matrix and the PL matrix. We can apply all of the values. We can take EI outside. We know that EI inverse is equal to 1 upon EI. We can add these two matrices. After adding, we are getting this. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to calculate the inverse in the calculator, see the description below. There is a link. You can click the link and watch the video for getting ideas how to make inverse in the calculator. I have used the calculator and found the inverse. Then we have to multiply these two matrices. We have to multiply the rows with the column. You can see the multiplication here. After multiplying, we are getting the final answers. We know that in this problem, the system displacements or the slopes which we got finally, the slope values will be according to the coordinates. The first coordinate is the point B. So first we will get theta B, which is equal to 4 upon EI. The second coordinate is the point C. So here we are getting theta C, which is equal to minus 12 upon EI. So in this analysis, we have found the unknowns. Now we can apply these two values in the slope deflection equations and find out the final moments. First, let us make the slope deflection equations in the span AB and find MAB and MBA. In the beginning, we have already calculated the fixed end moments. We can apply in all of the equations. In the point A, we are having a fixed support. In the fixed support, there will be no slope. So let us cut theta A and make it as 0 in both of the equations. The moment of inertia for the span AB is 1.5i. So instead of I, we have to apply 1.5i. The length of AB is 6 meter. We can apply that. When we apply the value of theta B in these equations, we are getting MAB and MBA. Now let's make the slope deflection equations in the span BC. No need to make the slope deflection equation for MCB because we already know MCB is equal to 0. Only make the slope deflection equation for MBC. In the span BC, the moment of inertia is 2I and length is 4 meter. We can apply them. After applying the values of theta B and theta C in this equation, we are getting MBC. Finally, we have calculated all of the moments. MAB is equal to minus 38 kilonewton meter, MBA is equal to 24 kilonewton meter, and MBC is equal to minus 24 kilonewton meter. In this beam, we have calculated all of the moments. For MAB, we have got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we have got a positive value. That means it is acting in the clockwise direction. For MBC, we have got a negative value. That means it is acting in the anti-clockwise direction. Now let us calculate the vertical reactions. First, I am going to take the span AB and find out the vertical reactions. In the span AB, we are having two moments, MAB which is acting in the anticlockwise direction and MBA which is acting in the clockwise direction. So when we calculate the reactions, we have to consider these two moments. In this span, first I am going to calculate the reaction RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive, anti-clockwise will be negative. RA is acting towards the point B in the clockwise direction, so it will be positive, and the distance is 6, so 6 RA. The point load 45 kN is acting towards the point B in the anti-clockwise direction, so it will be negative, and the distance is 4 meter, so minus 45 into 4. This movement is acting in the anti-clockwise direction, so it will be negative, and this movement is acting in the clockwise direction, so it will be positive. Finally, we are getting RA, which is equal to 32.33 kN. To calculate RB1, let us apply the rule summation of vertical forces is equal to 0. In this span, we are having three vertical forces, RA, RB1 and 45. RA and RB1 are acting upwards, so both are positive. 45 is acting downwards, so it is negative. We have already calculated RA, which is 32.33. We can apply that. Finally, we are getting RB1 12.67 kN. Now, let us take the span BC and find out the reactions. In the span BC, we are having only one moment, MBC, which is acting in the anticlockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. In this case, I am moving towards right hand side. Clockwise will be positive, anticlockwise will be negative. RB2 is acting towards the point C in the clockwise direction. So it is positive and the distance is 4 meter. So 4 RB2. The UDL is acting towards the point C in the anticlockwise direction. So it will be negative. When the UDL comes, we have to multiply with the distance and the distance by 2. So 4 into 4 upon 2. The moment 24 is acting in the anticlockwise direction. So it will be negative. Finally, we are getting RB2 is equal to 36 kN. Now let's apply this rule and find out RC. RB2 and RC are acting upwards, so they will be positive. 15 kN per meter is acting downwards, so it will be negative. When the UDL comes, we have to multiply with the distance to get the total load. When we do that, we are getting 60. RB2 we have already calculated. We can apply that. Finally, we are getting RC, which is equal to 24 kN. In the point B, we have calculated the reaction two times. Let us add both of them. After adding, we are getting RB is equal to 48.67 kN. Now let us make the shear force diagram. Before drawing the shear force diagram, let us calculate the shear force values. I am calculating the shear force values from the point A towards the point C. In this case, I am moving towards right hand side. Upward forces will be positive and downward forces will be negative. You can see the calculations here. Now let us make the shear force diagram. For the positive values, we have to draw the diagram above this line, and for the negative values, we have to draw below the line, and we have to mark as positive and negative. Now we are going to draw the bending moment diagram. For drawing the bending moment diagram, first we have to make the free moment diagram, then end moment diagram, then we have to combine both of them to make bending moment diagram. For making the free moment diagram, we have to consider every span as a separate simply supported beam. In the simply supported beam, if the point load is not acting on the center, we have to split the beam into two parts, A and B. The formula for the maximum bending moment under the load is WAB upon L. Here W is 45, A is 2, B is 4, L is 6. When we apply in the formula, we are getting 60 kN meter. If in the simply supported beam, UDL is acting for the full span, the formula for the maximum bending moment is WL square upon 8. Here W is 15, L is 4. When we apply in the formula, we are getting 30 kN meter. In the simply supported beam, we know that if the point load is acting, the bending moment diagram will be in the shape of a triangle. If UDL is acting, the bending moment diagram will be in the shape of a parabola. Now let's see how to make the end moment diagram. Using the end moments, we have to make this diagram. First, we have to draw these curves. MAB is acting in the anticlockwise direction, MBA is acting in the clockwise direction, and MBC is acting in the anticlockwise direction. Now we have to see the direction of the curve. All the three curves are indicating upwards, so the points will come above this line. Let us mark them, here 38 and here 24. In the point C, there is no movement, so here it is 0. Then we can connect. Even though we are having two movements in the point B, we have to make only one point because both of the arrows are indicating upwards. If the end moment diagram comes below this line, that will be positive. If it comes above the line, that will be negative. Right now, all of the values are coming above the line. That is why it is negative. Now we can combine the free movement diagram and end moment diagram. Wherever they are acting alone, we have to mark the sign with the values. If they are acting together, we are not marking anything. We just keep the space empty. If you are very experienced, no need to make the free movement diagram and end moment diagram. You can make the bending moment diagram directly. Now we are going to end this session. Thank you for watching this video.